Hello and welcome to this session in which we will look at some simple algorithms on graphs. In particular, we will look at what are called graph traversals. So, what is a graph traversal? As we have seen, the most basic question on graphs is given two nodes n and m, find a path in the graph that starts from n and ends at m. That is, we want to start at node n, move to some successor of n and keep moving to successors of nodes till we reach the node m. So, this is exactly the problem of trying to go from city x to city y by using an airline's connections that are available. There may not be a direct connection, but there may be a path from x to y, which is essentially a sequence of flights that you can take to reach from x to y. So, the representation of a graph gives us only local information about the graph. For every node, it tells us which nodes are its successors, or given two nodes, it tells us whether one is a successor of another. But the properties of graphs that we are interested in are mainly global properties of the graph. So, existence of a path, for example, is a global property. Just by looking at all the successors of a given node, we cannot say whether there is a path from a given node n to n. We need to go through list of all the nodes in the graph to say whether it is possible to reach a node n by a path starting from a node n. And a graph traversal is a systematic way of collecting information about the entire graph, and we gather the information by traversing the whole graph in a systematic way, and this information then can be used to solve many other problems on graph. So, we look at one such method which is called depth first search in a graph, which is a systematic way of visiting all nodes of a graph. So, while traversing the graph, we will gather information about it and use this later to solve many other problems. So, depth first search turns out to be the first step for many problems on graphs, and in many algorithms the first step that you perform is depth first search, and this is especially useful for finding paths and cycles in a graph and related problems. So, what is depth first search? So, we define a function called traverse s comma v. So, S is a sequence of nodes in the graph to be visited, and V is a sequence of nodes that have been visited. So, traverse will finally return us a sequence of all nodes that get visited, but it uses currently two sequences of nodes, one which is yet to be visited and V is those which have been visited. And the important point is it will return a sequence of nodes in a particular order, in the order in which they get visited during our traversal. So, this is similar to, for example, pre-order traversal of a tree, which generates a sequence of all nodes of the tree in a particular order. Similarly, depth first search generates a sequence of all nodes in the graph in a particular order. So, traverse phi comma v is v. So, if no more nodes remain to be visited, then we just return the list of nodes that have already been visited, and that is the final list of all nodes in the graph. So, traverse phi comma v is v. If the sequence of nodes to be visited is not empty, so there exists a node n, the first node n to be, which we know has not been visited, or which may or may not have been visited, we check whether it already occurs in the set of visited nodes. If it does, then we do not do anything, we just move to the next node in the sequence S. So, if a node in S is already occurred in V, then we ignore this node and do nothing. Otherwise, we will do what is called depth first search starting from node n and with the set of visited nodes V, and take that as our new set of visited nodes. So, the set of visited nodes is expanded starting from this new node n. So, we found a node n which was not visited, and we start what is called a depth first search from node n with the current set of visited nodes, and expand the set of visited nodes to be the set n comma v, DFS n comma v, and then traverse the remaining sequence of unvisited nodes in S. And DFS essentially to starting from node n, all it does is it adds V to the list of visited nodes. So, a new sequence of visited nodes becomes obtained by concatenating V and the sequence push n comma phi. So, we add n to the end of the sequence of visited nodes V, and that is our new list of visited nodes. And now we traverse through all the successors of the node n, and again check if any one of the successors has been visited or not. So, if you find a successor which has not been visited, it will again call depth first search for that successor, and again it will push that successor into the list of visited nodes and so on. So, this is a compact way of describing depth first search in a graph. Essentially, we keep expanding the set of visited nodes. Every time a new node is found which is unvisited, we start a depth first search function from that. All that depth first search does is it adds this node to the set of visited nodes, and it calls depth first search for the successors of itself. So, traverse S comma phi. So, when we start with the set of all nodes in the graph and empty set is the initial visited sequence of nodes, this will return all nodes in the graph in the order in which they get visited. On the other hand, DFS n comma phi will return a sequence of nodes to which there is a path in the graph from node n. So, if there is no path from node n to some node, it will not get added to the sequence DFS n phi, and this is something that you can prove by induction. By just looking at the definitions of these functions, can show that only if there is a path from node n to node m will node m appear in the sequence DFS n phi. So, the function that we have defined only tests whether there is a path in the graph, but we can modify it to actually return the sequence of nodes in the graph from node n to node m. And we usually need to do many other computations apart from ordering the nodes in the graph while doing depth first search. So, alternatively we can write this in a more programming style. So, here DFS n comma phi constructs a tree with root n of nodes that are reachable from n. So, instead of returning just a sequence of nodes, now DFS n phi is actually returning a rooted tree with n as the node, and it will essentially return a tree of all the nodes that are reachable from node n in the graph. And then the path from any node in this tree to n can be found by following the parent array in this tree. So, for every node we will find its parent in this tree, and that we will finally come back to the root node which will be n, and that will give us the path from n to any node in this tree. So, initially the tree contains only the node n and no subtrees. The list of subtrees is empty, and we add n to the list of vertices which are visited. So, DFS NV just modifies the set of visited vertices, and it constructs a tree and returns the tree as a return value. Then all that we need to do is look at all successors of the node n and pick any element I in that list of successors. If m has not been visited, if it does not belong to the sequence V, right, then we attach the or we call DFS m with the new list of visited vertices, that returns a tree, and attach T itself to attach to the tree T the new tree that has been returned. So, that is a new subtree that gets attached to the list of subtrees of the tree T that we have got. Initially, when we had no subtree to that, when a successor is found which has not been visited, we will call DFS for that successor. It will return some subtree of nodes reachable from that successor, and we will attach that as a subtree of the tree T. Finally, we will return the tree T. So, this is a more programming style of describing depth first search. It is much more compact if you use the functional description, but this is more powerful. You can do more things like computing the parent and so on using this. There is an alternative way of traversing a graph. So, just as in tree we had pre-order, post-order, this is a different way of traversing a graph which is called breadth first search, and this is especially useful when we want to find a path with minimum number of nodes from a given node to another node. So, depth first search will just give you one possible path from node n to node m, but it may be a very long path. So, if you are using it to find a flight from x to y, we may end up going through a very roundabout way. but then breadth first search is a better option, which gives the shortest possible path from a node n to node n. So, this is also defined in a similar way. We have a list of nodes to be visited and a list of nodes which have been visited, and we define the traverse function in a similar way. If node n has already been visited, then we do nothing, we just traverse the remaining sequence of nodes. The list of visited nodes remains the same. If node n has not been visited, then we call breadth first search from this node, and we will add a new set of nodes to the visited set of nodes. So, the visited sequence now will be defined by BFS, and BFS will be obtained by concatenating the node n to the set of visited nodes, and we will add n to another sequence which is a Q. So, BFS takes two parameters V and Q. V is essentially the set of visited nodes, Q is a set of nodes which we have visited, but whose successors may not have been visited. So, the property is that V contains all visited nodes, Q contains nodes which have been visited, but whose successors may not have been visited. So, this is what breadth first search with view. If the queue has become empty, that is that all nodes have been visited and their successors have also been visited, then we just return the sequence V of the set of visited nodes. Otherwise, we pick out the front element of the queue and remove it from the queue. Look at all successors of that element n. If some successor does not occur in the sequence V, so that is it has not been visited so far, then we add this element m to the sequence V, insert this element in the queue, because now we do not know whether successors of m have been visited or not. So, we will also insert m in this queue, and in this case again we set parent of m equal to n. So, this will again define a tree called a breadth first search tree. Finally, we return the sequence BFS BQ after modifying V and Q in this form. So, this is an alternative way of traversing a graph. Now, we can use the similar ideas for many other problems on graphs. So, we consider what are called directed acyclic graph. So, a graph is acyclic if it does not contain a cycle. So, many graphs in different applications are required to be acyclic. So, for example, graph of course prerequisites cannot have a cycle, because that would mean that you cannot start on any of those courses. Every course has a prerequisite which is in the cycle. So, then there is no course that you can start on that at all. So, this graph surely cannot have a cycle. So, property of such graph is what is called a topological ordering. So, it is an ordering of the nodes of the graph such that every ordered pair nm corresponding to an edge, n occurs before m in the ordering. So, all the edges of the graph go from a node which occurs earlier in the ordering to a node which occurs later in the ordering. And such an ordering can be used to solve many problems for directed acyclic graphs, and we can use depth first search to find this ordering. So, here is a simple definition of top sort similar to this. So, this is exactly similar to the traverse function. We will again call DFS if the node has not been visited, and add the set of nodes that get visited to the set of visited nodes NV. The only difference here is in the DFS, instead of pushing the node into the set of visited nodes right at the beginning of the call to DFS, we do it after looking at all its successors. So, we will first do depth first search on all the successors, that will end up visiting some other nodes, and then the node n itself is added last to the sequence V, or it is added at the beginning of the sequence V. So, instead of adding it at the end of the sequence V as we were doing previously, we will add it to the beginning of the sequence. So, in this case the nodes in V will actually appear in the order in which DFS was completed for that node, rather than the order in which the nodes were visited. So, this gives a different ordering, but this will have the property of a topological ordering if the graph is directed acyclic. So, this will give a valid ordering if the nodes in the graph is acyclic. However, it does not check whether the given graph is acyclic. So, after you have got the graph and you have got this ordering, you can go through the list of edges and check that every edge goes from a node which occurs earlier to a node which occurs later. If it does not, then this graph is not acyclic, and you can modify this function to actually find a cycle. So, you can try that as an exercise, and this completes our session on graphs. We will see more about graphs when we consider implementations and algorithms on graphs. Thank you.